bases and pH. So let's figure this all out. And maybe if my pen would work, it would help. There we go. Okay. Acids and bases and pH. Okay. So the first thing that we're going to talk about, and we're going to look at this in a very simplified manner, I guess. So if you're looking for advanced acids and bases, this really isn't going to cover that. So the first thing to understand here is the actual nature of water. All right, because acid and base chemistry is related to the chemistry of water. All right, water is a pretty ubiquitous, in other words, it's everywhere, compound on the Earth. I mean, 70% or more, I think, of the Earth's surface is covered by water. So a lot of the chemistry that pertains to living things, happens in an aqueous or in a water environment. All right, and acid and base chemistry is important inside the bodies of living things as well as outside the bodies of living things. So it's good to have an understanding of this important, element that compound, that if it weren't around, living things wouldn't be around, right? We owe a lot to water. So let's look at water quickly. So if you remember, we were to draw out the Lewis dot diagram for water, you get this kind of a shape, okay? We're not going to go into the really deep chemistry here, but I will tell you that in water, oxygen, right, is acting and it's a nonmetal, and therefore it attracts or has an affinity for electrons, okay? So this is a new word, electron affinity. Oops, electron affinity. What that means is oxygen pulls electrons towards its nucleus. It holds them tight to itself. Okay? So in water, what ends up happening is the electrons from hydrogen, as well as oxygen's own electrons, end up much closer to the oxygen than they do to the hydrogen. Okay? And the other thing to remember is, what is hydrogen like? Well, hydrogen is simply a nucleus, but that nucleus is only a proton. The whole nucleus of a hydrogen is just a proton. And it's got an electron zipping around, right? Kind of existing around that outer or that inner shell, I guess. And so what that means is, if this electron gets kind of pulled away from here and spends its time much closer to another atom, such as oxygen, that means that there is like a partial sort of positive charge floating around this, right? So if we imagine that instead of this electron zipping around back over here, it kind of gets pulled into this bond and stays inside here, we can imagine that water is going to have sort of a positive part over here, and this little symbol just indicates that it's not a true ionic charge, but it means that there's a polarity to this molecule. Polarity like the poles on a magnet, right? Or the poles on a battery, if you want, right? One side's positive and one side's negative. The overall whole is neutral, but the actual, charge distribution around this molecule has it set up like that, okay? So that's very important. Now, we noticed that when we put an ionic compound into water, the fact that this molecule is polar, right, it's got a partial positive and a partial negative side, was able to take ionic compounds like, say, NaCl, for instance, and surround the Na with water molecules, right? So Na, we know, has a positive charge. It's lost its electron to chlorine. So in that case, you'd have the O side surrounding sodium, and then you have your positive side, and actually both of these are kind of positive, surrounding the chlorine. So what you get is, you get kind of like this situation. You get your Na, you get your Cl, and then all around the outside, you're going to end up with, these little water molecules lining up all around. I'm drawing like little V shapes, just indicating that it's sort of like a V shape, like that, okay? And then separating these charges away from each other. Okay, this is going to be important in a second here when we get into what's going on with acids and bases, all right? So this is the act of dissolving. Now remember, because sodium was carrying a positive charge and chlorine a negative charge, you now have what are called ions, like floating freely around in a pool of water, right? So if we imagine then, if we bring this up from micro scale or like the miniature world of atoms and things that are really small, we can say that then if we add NaCl to a whole cup of water, it will dissolve in there and we get what we call salt water, right? Or just an ionic compound dissolved in the water all through here. You get all these ions floating freely around. And that has effects, right? It makes that an electrolyte. So in other words, the water can now pass electricity. I mean, it would taste salty. I don't know if you'd want to drink the solution of all ionic compounds, but definitely, I mean, you could taste salt water. I wouldn't want to drink it, but you could taste it, and so on, okay? So that's kind of the background. Now let's talk about water itself and what happens in a pool of pure water, and then we'll get into pH right after that. So let's say we have a beaker filled with water, all right? So we have that OHH water sitting in there. Now here's something that happens that's kind of interesting. So to say that something is either completely molecular or completely ionic is a bit of a generalization. In fact, really what happens is deciding whether or not a bond is ionic, so if I have NaCl, or covalent, really depends on the difference between the electron affinities of the two species involved, the two atoms involved. So we could say then, in something like NaCl, this is a very low affinity for electrons. It's not very good at hanging on to that electron that's moving around it, right? And therefore it has a tendency to lose the electron. Whereas chlorine has a very high electron affinity. Okay, and we're just going to say electron affinity. That's shorthand for electron, just an E negative. Okay, and because there's such a vast difference, okay, we're going to say this is an ionic compound. Now, if we go to the other end of the spectrum, and let's say we just have something like Cl and Cl. Now, both of these have an equal electron affinity, right? So what we can say then is there is no difference between the electron affinity. So the electrons that are in this bond, right, essentially rest exactly halfway between the two atoms, all right? Here, the electron gets like pulled all the way over here, and we say it's an ionic because it gets pulled right off, essentially. We call it an ionic bond. Whereas this one, this set of electrons sits in the middle and shared in between, right? It's exactly halfway in between. The electrons aren't closer to one or the other because they're equal. Well, we say that's a covalent bond because they're equally pulling electrons towards themselves. Now the question is, okay, well, what happens if we get a situation where one pulls, but it doesn't pull quite hard enough to be considered truly an ionic bond or to be considered truly a full covalent bond? So what do we say there? Well, with water, what ends up happening is that oxygen is strong enough that some of the hydrogens actually go off and become ions, okay? So how does that work? Well, essentially we just look at it in terms of numbers, all right? So every once in a while, instead of being a molecule, you get a splitting of the water into an OH minus, that's what would be left over, and then the loss of an H plus, okay? So in a sense, right, water is dissolving in itself. I know, it's weird. It's weird to think of that, but a little bit of water, just natural everyday water, has separated into two ions, okay, and they have names. This is a hydroxide ion, and we've seen it before, right? We've seen a hydroxide ion before. It's on our table of common ions. And then the other thing is H plus, which is a proton. Now we will recognize that ionic compounds, which have an H on them instead of the metal, we call those acids, right? You know, and there's all different kinds, and we looked at how to name them and so on. So there's a relationship here somehow between what water normally does and then dissolving something that when it gets put into water adds more H pluses to it, right? Or on the other side of the fence, if we say talk about bases, and we'll look at how to recognize these in a second, but if I take an ionic compound that has a hydroxide ion, it's going to add more of these when I dissolve it, okay? And now we're kind of getting at the principle behind why something's an acid and why something's a base and how it relates to water itself. Okay, let's say we could have something like this. Okay, both of these are bases, both of these are acids, and they are related to what water naturally does on its own. All right, so now the question is, well, how much of normal water is ionized? Okay. All right. How do we measure that? All right. So how much of water is in this form as a molecule, and how much of water is in this form as ions? Okay. So we're going to introduce some more new stuff here. This maybe isn't the best place to do this, but I kind of need to talk to you about the mole. So the mole is not an animal. The mole is not a mark on the skin. I mean, they are those things, but this is the mole, the MOL mole. So what is it? Well, a mole is a unit of measurement. All right. We're not going to get deeply into where it comes from, but essentially we're going to say this. Well, maybe we will. So how do I do this without like basically it's this. Okay. Here, how about this? It's kind of like a liter. No, not really a liter. It's kind of like a dozen. Yeah, it's kind of like a dozen. In that, it represents a number of something. It represents a number of something. Okay? So like you could say go to the store and buy a dozen eggs and you'd know you were getting 12 eggs. Or you could go to Timmy Ho's and you could get a dozen donuts and you know you're getting 12 donuts. Or you could go get, you know, a baker's dozen of muffins and you'd know you're getting 13 muffins. Yeah, I know. Doesn't make sense. But I guess they put one extra in just in case one gets ruined. I don't know. So what's the mole have to do with a dozen? Well, a mole is like a dozen because whereas a dozen is equal to 12 things, a mole is equal to 6.02 times 10 to the 23 things, which is a lot of things. So the question is, why do you ever need a number this big? And actually, this number has a reason. There's a reason why it's this particular number. And basically, it goes like this. So there is an isotope. I guess we haven't used that word yet either. But there's an isotope of carbon called carbon-12. Okay? So what does that mean? Well, it just means this. If I look at the periodic table and I see carbon, I can figure out that there are 6 protons in carbon. Okay? But if I look at the atomic mass of carbon, I see it's like 12.01, right? It's got this little like weird 1 on it. You might say to yourself, well, why would it have a little 1 on it? Because I also think it has 6 neutrons in there, right? But it turns out there's some other versions of carbon called isotopes that actually have different numbers of neutrons in them. So for instance, there's a version of carbon called carbon-13. And you guessed it, 13, it has 7 neutrons. But almost no carbon is like this. Only a tiny fraction is like this. There's actually other carbons as well, like this, carbon-14, etc. Now, some of these are radioactive and are used in radioactive dating. I think it's carbon-14 that's radioactive dating. But the point is just this. These are called isotopes. They behave chemically the same as carbon because they have the same number of electrons in the outer shell, but they just have different weights. And it turns out that the nuclei can be unstable if this ratio is off, all right? Now, that's not the point of what we're talking about because we want to talk about the mole. So you take the isotope carbon-12, right, and you weigh it. And what scientists have done is they figured out that if I get exactly 12 grams of this stuff and I count the atoms very carefully, it turns out that in exactly 12 grams of carbon-12, there are, you guessed it, 6.02 times 10 to the 23 carbon atoms. They're very, very small, so you only need 12 grams to get this value, okay? It's also called Avogadro's number, by the way. You might hear it called that as well. And so what this allows scientists to do is it allows them to look at other atoms, okay, and weigh them relative to carbon, and then figure out that, you know, in those other values, or I guess what you could say is you could say that the numbers that you need to get a whole mole are equal to the atomic weights, right? So what we get from that is if you say switch now to hydrogen, right, which has 1 proton, in 1 gram, you have that 1 mole or that number of atoms in there. And you do that with all the other elements on the periodic table. You weigh them relative, okay? So that's what a mole is. That's what isotopes are. And we started this all off by talking about acids. We're covering a lot of ground today. So where does it come in with acids and pH? So if you remember, in order to talk about this pH business, we had to look at moles, and we also have to look at logarithms, which isn't going to take long, don't worry. But it turns out that in normal water, in normal everyday water, okay, so this is going to represent a jug of water. Most of the water is in molecule form, but a little bit is separated into this. Just a little bit of it. So the question is, how much? Well, 1 times 10 to the negative 7 moles for every liter of water is in H plus and OH minus, okay? So 1 times 10 to the negative 7 moles, okay, of hydrogen is in ion form in water. And then because there's an equal amount of H plus and OH in regular water, there's also that number of moles of OH minus. So 1 times 10 to the negative 7 moles per liter of H plus in normal everyday water, 1 times 10 to the negative 7 moles per liter of OH minus in regular water. Here, I'll make this look more like an L so it doesn't look like a 1. Okay? Okay. Now, where does the number 7 come in when we talk about acids and bases? Have we seen this before? We talked briefly about that. 7 is like the magic number when it comes to acids and bases. Any value lower than 7, means that we have an acidic pH, and we'll see why in just a second. Any value higher than a pH of 7 is basic. So 1 times 10 to the 7, okay, if we take the log of this value, the logarithm of this value, we get the number 7. We take the log of this value, we get this number. Can you guess what a logarithm is? If we take the log of this value, we get this value. Okay? All a logarithm is what number you raise 10 to get the number you're interested in. Okay? So the log of 100, log of 100 would equal what? What do you think? What do I raise 10 to get 100? 2. So the log of 100 is 2. The log of 1,000 is 3, etc. So that's what a logarithm is. Simple, right? So what's pH then? Well, pH is like a regular logarithm, okay? But the P symbol simply means the negative logarithm of some value. So if you look at pH, you got a little p, and then you've got an H. Well, H is representative of H plus. We're almost there, okay? So we've got this. If I put a P in front of the H, what I'm saying is I need the negative log of the concentration of H plus ions, which we just said was 1 times 10 to the negative 7 moles of H plus per liter. Well, the negative log of negative 7 equals 7. Boom. pH of normal water is 7. Why? Because the negative log of the hydrogen ion concentration, that's this H right here, this represents H plus, so it's the P of the H, the negative log of the H value, okay? The negative log of that is 7. So here's where acids and bases come in. Let's say I have my regular water. Here it is. There's my pH water of 7, regular everyday water, pH of 7. What that means is, in that regular water, the H plus concentration is 1 times 10 to the negative 7 moles of H plus per liter. Now let's say I take some hydrochloric acid, and I start to dump it in there. Well, now what I'm doing, when I put it in there, right, it splits into H plus, and it splits into Cl minus, and the amount of H plus in there gets higher and higher and higher. So the concentration then gets a negative value that's lower, right? Because these are actually larger numbers. A lower value in the negatives means more stuff, right? Just like 100, 10, 1, 0.1, 0.01, and 0.001, etc. Well, this is 1 times 10 to the 0. This is 1 times 10 to the 1. As we get bigger, right, we get larger. But down here, right, this is 1 times 10 to the negative 3. 1 times 10 to the negative 2. As we get more, this number gets lower because it's a negative number, 1 times 10 to the negative 1. So this number is getting lower. But if we put the p in front of it, we want the negative log of this number. What comes out the other end? Well, the pH equals 6 if we add more of this, right? Then the pH equals 5 if we add more. As I add more and more acid into the water, the pH gets lower and lower and lower and lower, doesn't it? Etc. So we're going to finish off tomorrow with, well, what happens if instead of adding acid, I add something with this on it? What's going to happen there? So that's for tomorrow.